Okay, so let's take a look at the second page here. In the second page, instead of talking about doubling period, it's talking about half-life. So you can only imagine if it's talking about half-life, it's going to describe, half-life describes when something is being cut in half or how long it takes for something to be cut in half. So just like doubling time, the common ratio was double or 2, the half-life, the common ratio will be a half. So that's what the base will be. So let's take a look. You can read this yourself. Let's take a look at example 2. All living organisms contain a known concentration of 1 part per trillion parts of carbon-14. Carbon-14 is a radioactive element. It is used to date ancient artifacts because it has a half-life about 5,730 years. So it takes 5,730 years for carbon-14, this radioactive element, to cut in half. Okay, so it's not per year that it's cutting in half, it's every 5,730 years that it cuts in half. The formula for this carbon-14 is this right here. And it's used to calculate the concentration in parts per trillion remaining after n years after death. Okay, so what would the concentration of carbon-14 in a piece of cloth made from plant fibers be after 5,730 years? So taking a look at this formula, the amount of carbon-14, and I'm going to put n in terms of time, is equal to, now it has the base of a half and it has n all over 5,730 years. So the way I read this, just like I read any of the other ones, so just like I read y equals a times b to the power of x, remember that your a value is your initial or starting amount of whatever you're dealing with. In this case, the initial out in front of here is 1. Now we don't write the 1, but that's what it is. That's what you start off with, 1 radioactive element of carbon-14. Your b value is your base or your common ratio, okay? And your common ratio in this case is half because it's the half-life. The thing is being cut in half every so often. And x deals with time per, and then usually it's per year or per hour or whatever. This case, this thing is being cut in half every 5,730 years, okay? So this is happening per 5,730 years. So every 5,730 years, this carbon-14 is being cut in half. So if it asks me to figure out how much carbon-14 there's left after 5,730 years, all I'm going to do is plug in 5,730 into this equation, and I'm going to have a half 5,730 all over 5,730. So guess what? This carbon-14 at 5,730 years, it's being cut in half once because that divided by itself is just 1. So when I figure this out, the amount of carbon-14 after 5,730 years, 1 times a half is just a half, so 0.5. So there is 0.5 of that carbon-14 after 5,730 years. Okay? And so then it asks me to figure out what is the amount of concentration of carbon-14 in animal bone after 50,000 years. So figuring that out, all I'm doing is plugging in 50,000 in for n. So plugging in 50,000, this is going to equal 1 times a half to the power of 50,000 all over 5,730. So continuing this, it's not going to be a nice answer, but it's going to be 1 times a half, and then I'm going to do on my calculator 50,000 divided by 5,730, and I'm going to get roughly around 8.726000349. Okay, and how would you do this on your calculator? Well, just plug this in your calculator to figure out how much carbon-14 there's going to be. And so you're going to do 0.5 to the power of, and in that case it's 8.726000349, and you're going to get roughly 0.00236, let's say. So that's how much carbon-14 will be remaining after 50,000 years. Okay, I have a couple other questions that I'm going to do here. The first question would be, how about if you have something that looks like this? So example 3, a car depreciates, by 15% per year since it was purchased. If the car was purchased in 2010 for $32,000, how much will it be worth in the year 2015? So let me just come up with a table of values here, and it's going to talk about time and the value of the car in terms of time. Now, I know that in the year 2010, which is time 0, the initial time, the value of the car is $32,000. Okay? And what I'm trying to figure out here is how much the car is worth in the year 2015 according to this depreciation. Now, if you're depreciating by 15%, that means you lose 15% per year. Okay? Now, if you lose 15% per year after the first year, how much will you have left? Well, you only lose 15% of this, so the first thing would be to figure out 15% of this, which is multiply this by 15%. And if you just do that on your calculator and multiply by 15%, you're going to get that it loses $4,800. So there's a $4,800 loss. It doesn't mean that it's worth $4,800 after the first year, because that would be pretty much insane. It's going to be it's going to lose $4,800. So what you're going to do is you're going to take $32,000 and subtract $4,800 from it, and now the car will be worth $27,200. Okay, and you can continue this on and on and on for every year it loses 15% of the previous year. But in order to come up with the base of this function, or the common ratio, you have to do this divided by that to figure out what the common ratio. Now, if you did 27,200 divided by 32,000, you're actually going to get 0.85. And that goes along with the same thing as if you found more values here. Why is the car only worth 85% of the previous year? Well, if you take a look at this, if it didn't depreciate and it was worth 100% of the previous year, it would always be worth 32,000, 32,000, 32,000, worth 100% of the previous year. But if you're depreciating by 15%, it means you have to subtract 15% from 100, from 1. And so 1 minus 1,500 would be 85%. So you are now only worth 85% of the previous year. So the correct formula for this, coming up with A times B to the X, the correct formula for this would be value of the car in terms of time is equal to the initial amount is $32,000. That's what always goes here. Your base is the common ratio, which is 85%, and to the power of time. And now it's time over 1, right? We don't write the 1, but it is time over 1 because this happens per year. Okay? It's per year. So this is the correct formula to figure out any year. Now, if you want to know what happens in the year 2015, how much it's worth in the year 2015, that is 5 years later. So I'm not going to plug in 2015, I'm going to plug in 5. So this is going to be value of the car 5 years later is equal to $32,000 times 0.85 to the power of 5. So just remember, when you go and do this math here, that you do not multiply the 32,000 by 85% first. You're going to do 85%, so 0.85, to the power of 5 first. Then you will multiply by 32,000, because that is the order of operations, and you should get $14,198.57. This isn't too far off of reality, because cars usually depreciate by about 15% a year. Okay? And so that's the correct answer to this one. First come up with the formula, then come up with how much it's worth afterwards. So you don't have to show this work here. Just understand that if you're depreciating by 15% a year, the common ratio is 100 minus 15%, which is 85% of the previous year. And let's take a look at the last question I have for you here. The last question I have for you here is the half-life of Advil is 8 hours. Okay? So the half-life of Advil is 8 hours. So it's talking about half-life. Remember what half-life means. It means that your base is a half. Things are being cut in half every so often. So let's see what it's asking. If the concentration of Advil in someone's blood is 0.1 milligrams per milliliter at 8 a.m., what will the concentration be at 6 p.m.? Okay, so it's talking about concentration of Advil and how many hours are going by in half-life. So if you did come up with a table of values, you would have time, and you would have, let's say, the concentration in terms of time. So if you're coming up with concentration in terms of time, you know at time 0, okay, you have 0.1 milligrams per milliliter. That's the concentration. That's 8 a.m. Time 0 is 8 a.m. So if I come up with a formula here, y equals a times b to the power of x, I'm coming up with concentration in terms of time is equal to the initial concentration is 0.1 times the base. The base, well, it's half-life. So you're cutting this in half, and you're cutting this in half every so often. Now, the half-life is every 8 hours. So you have to be careful. This is not just to the power of t, it's to the power of t over 8 because it's being cut in half every 8 hours. So per 8 hours, just like all the other ones. So this is the proper formula for figuring out the concentration of that drug in your system. Now, they want to know what the concentration of the drug is at 6 p.m. It's very important you are able to count the hours from 8 a.m. to 6 p.m. Well, 8 a.m. to 8 p.m. would be 12 hours, so that means 8 a.m. to 6 p.m. is only 10 hours later. So I'm not going to plug in 6. It's very important you are plugging in 10 to this formula. So if I plug this in, this is going to be concentration 10 hours later, which is 0.1 times a half to the power of 10 over 8. So concentration 10 hours later is going to be equal to 0.1. And you can just use a calculator here. You don't have to use exponent laws if you don't wish. And you could just do 10 divided by 8 and write that as your fraction. Instead, you want to write it as a decimal. That's fine. That's 1.25. Okay. And just remember, you have to do a half to the power of 1.25 first. So when you figure out the concentration at 10 hours later, you're going to have to go 0.5 to the power of 1.25 first. So it's going to be 0.5 to the power of 1.25. Sorry here, 0.5 to the power of 1.25. And then you're going to multiply that by 0.1. And you should get roughly 0.042, let's say. So after 10 hours, you will only have 0.042 milligrams per milliliter left in the bloodstream. Okay? So it's very important you understand how to come up with the formula first and then answer the question according to the time 0. Okay? So now you have enough information to figure out all your homework.